Well, good morning, dear, and welcome back. Today, we are going to discuss, as you know, with all the basic materials um, digested properly, I believe. Now, today, we are going to really design a real robot, which is known as Puma. And another robot we'll also deal with in the next lecture, that is Baxter. So let us start. So as you know, this is Puma, made by Unimission Company initially. There are so many different model. We are talking about Puma 560 model. Okay, they the models differ a little bit about some of the geometrical parameters. And this is another robot, very interesting, and we'll also dissect it. I will tell you the anatomy of this robot as well. You will study that, and that is known as Baxter. And in our lab, we are calling it Onukul robot. Okay, it is developed by Rethink Robotics. This is a cobot, that is collaborative robot, and it has some special issues. That's why we will discuss in detail about Baxter also. But first, let us discuss about the grammar of robotics, that is the PUMA, Programmable Universal Machine for Assembly. And let us start from, now we are applying the Dinovet-Hartenberg notation and thereby principle, whatever you have learned, okay, we'll apply to our real robot Puma. And as usual, somebody has designed this. What is your assumption? Puma has been designed by some design engineer with all these parameters are given, okay, but no coordinate frame, etc., nothing is given. Only physical robot, Puma robot, is given to you. After getting the robot, after getting any robot, what you should do? Your task is to develop the planner. That is, your task is to model the robot. But for modeling, you will have to study its anatomy. Means you will have to dissect it. Okay. Here, let us see. So this is, Puma is just like, as I told you, it is our hand. Okay. Now, how many degrees of freedom it has? 6 degrees of freedom it has. Why 6 degrees of freedom it has? Because for capturing pose in 3D, pose means position and orientation, you require minimum 6 degrees of freedom, okay, robot. Otherwise, you cannot capture arbitrary pose in 3D. That's why Puma has 6 degrees of freedom. First, you need to identify where are those degrees of freedom, okay. Say, now, look here, this is my Puma robot. If you stand up on your feet and then twist your body clockwise and anti-clockwise direction, that is analogous to the motion of the Puma about this axis, you see. So Puma has a base, okay. This is what? And the length of the stand, okay, you can tell like Puma body, this is our, just like our leg, okay, our body, 660.4 millimeter height from the ground to the shoulder. So this is called shoulder joint. Now, you see, so Puma can move about this axis, about the vertical axis, just like you can move in a stand-up position, anchoring your feet in clockwise, anti-clockwise. That means your body can twist. So this motion is just like that. And then Puma has a shoulder. This is called shoulder joint, okay. So this is vertical axis, vertical column, and here is its shoulder. And with and this is the entire this entire part, okay, is one structure, okay. So whenever there will be motion, the entire structure will go up or down depending on, okay. So we call shoulder up, down. So this is shoulder motion. So another motion which you have identified here is this, okay. Now, this is called elbow, just like my elbow, this is my shoulder, but the only difference is my shoulder may have uh, more than 1 degree of freedom, but in case of robot, typical robot, one joint has 1 degree of freedom. Otherwise, control will be very, very difficult, modeling will be difficult. So, shoulder joint has 1 degree of freedom, okay. What is that degrees of freedom? This is the motion about this axis, okay. So shoulder can move up, down, okay. Then shoulder is connected with another joint. This is called elbow, okay. So elbow can move in this direction, up, down, okay. So elbow, just like my through elbow, my hand. So this is PUMA analogous to PUMA arm, okay. Elbow, this is elbow joint and PUMA arm. So it can move like that, okay. So this identifying all this motion is very important, and the moment, of course, it will be given, you already you will know that, okay. But I am trying to tell you these are the motion. So elbow is again another moving up and down. So there is a joint, elbow joint. Now, most interesting thing is PUMA gripper, this, okay. Here, so how many degrees of freedom so far you have discovered? One about the vertical axis, another about shoulder axis, another about elbow. So these are three. Another three is embedded in the wrist. There is a beautiful story behind it, why PUMA has done like this. Piper, D. Piper, his name, graduate student doing PhD in Stanford, he showed that in a serial open kinematic chain, if any three joint axes are intersecting at a point, then closed form kinematic solutions will be guaranteed. Normally, you see, you have a 6 degrees of freedom robot like PUMA, not like PUMA, any structure you can design having 6 degrees of freedom, okay, like this. Why not like this? Okay, I'm just schematically doing 1, 2, 3, 4, 5, and then 6, okay. You can do that, but there will be no guarantee that you will be able to solve it analytically. Is closed form kinematic solution, inverse kinematic solution will not be guaranteed to be a closed form. But Piper told that if any three joint axes, successive joint axes are intersecting at a point, then closed form kinematic solution, inverse kinematic solution will be guaranteed. So that's the reason this is industrial robot, and industry people who are very conservative. They want that, okay, if at all we need to solve inverse kinematics, okay, which is very required for program control robot like PUMA, then let us make this wrist like this. By the way, you see, in our maybe through millions of years of adaptation, look at our hand. PUMA was very much inspired by our hand actually. Look at here. Our wrist also has 3 degrees of freedom. What are those? Embedded at one point, you see. This is called yaw. And this motion is taking place with respect to a vertical axis like this, okay. This is a vertical axis, about that, this yaw. Then consider another vertical axis another vertical axis, and this is called pitch. My hand, I don't know whether it is visible. Yes, I think. So this is pitch. And consider another another axis of rotation about which this is called roll. So this is roll, yaw, and pitch. They are also intersecting at a point. I don't believe that we are solving inverse kinematics. It's a learning process. But you see, structurally, our body is also same, the way Puma's wrist has been designed. This is another issue that apart from gripper, we have several finger having redundant joint. Okay, not all joints, not everybody can move them independently, but in synchronization, they give enormous dexterity. That thing we will discuss later on, but very interesting. Additional degrees of mobility will give you dexterity, but Puma at least has not additional degrees of freedom, just required degrees of freedom. 3 elbow, shoulder, base, and 3 at the gripper, at the wrist. Not gripper, at the wrist. This is, we are calling wrist. So that we will dissect the wrist more carefully, because from here you cannot see much. We have just taking a, we are drawing, making a drawing, looking from this side, and then taking the elevation on this 2D plane. So we are representing all this structure here. Okay, looking from here. You are looking from here. The elevation we have on this plane. Okay, we are looking on this plane. Okay, you can call the elevation we are taking, and we are representing it so that you can clearly understand what are the complexity here. Okay, so you see here, this is one joint. So Puma has one rotation about vertical axis. You see how these are the three joint axes at this point. Okay, you can see Z4, X4. This is Z5, X5. Z5 is perpendicular to the plane of the board. Okay, and here also you can see Z6. So this is Z6. If it is not clear, this is Z5 is perpendicular to the plane of the board, and this is Z4. Okay, and unit vector. That's why it is like this. And here also perpendicular to the plane of the board is Z3. So 3, 4, 3, 4, 5. This is 5 Z axis also perpendicular to the plane of the board where this has been represented. Clear? Okay. So this is actually one axis passing through the. This is the. Okay. So this is Z. This is Z4. This is Z4. Okay. And about this Z4 you can rotate. That means entire this portion will be rotated if you rotate about Z4. Okay. Okay. And then this Z5, about Z5 you rotate, this is called yaw. Okay. So this part together with this will move like this. Okay, when you rotate about Z5. Is it clear? Okay, Z5. Z5, entire this lower assembly will. And then Z6. Z6 is the angle axis. Okay, I will just show you. You see, yeah, only this part will rotate. So this will rotate. Okay, and then with this, when this is called yaw motion, when Z5 will rotate, then with this the entire assembly will rotate up and down. And with this, when Z4 will rotate, this is joint. Okay, so the entire assembly will rotate like this. So these are the three motion which has been embedded at the PUMA wrist, and that's the beauty. Okay, and making it anatomy much more simpler in the form. Here you can see, yes, this is very, very important. So this is, we have given it here. Okay, so this is roll, this is roll about Z6, this is pitch about Z5, this is yaw, this is yaw, and there. Okay, so 4, 5, 6, 4, 5, 6, 3 Z axes are intersecting at a particular point. Okay, they are giving yaw, roll, and pitch motion to the PUMA wrist. So the 3 degrees of freedom here, 1 degree of freedom in the elbow, another is on the shoulder, another is on the base. Having understood this motion, it is very important to understand that where to fix the, now I know, moving around that PUMA robot, I know what are the motions available, and they form a very crucial role in attaching the coordinate frame, as you know, right? Now, see, I can attach coordinate frame at the base here, the 0th coordinate frame. Say this is x0, z0, and incidentally, okay? So about that, I could measure the θ1 angle, and 660 millimeter geometric, this is the height from the base to the shoulder, is that height. Also, I have an option that since this is entirely a rigid body, I can put 0th coordinate frame here, attached with this base. And in doing so, what I can do, since it's a rigid body, so I can, if I now put my Z0, okay, X0, Y0, perfectly aligning with 1, but attached with this, what I can do, I can get any points position vector when all this transformation matrix will be given. I can describe any points, arbitrary points, position vector with respect to 0th coordinate frame, whether it is attached here or here, it hardly makes a difference. Only thing here, additional parameter will come that I do not want. So that's why initially let us put the coordinate frame, 0th coordinate, ith coordinate frame is here, first coordinate frame, okay, and completely aligned with that, I am putting 0th coordinate frame, okay. You should be able to appreciate, okay. Now, another coordinate frame is required. So this is 0th coordinate frame and first coordinate frame. Okay, 0th coordinate frame is attached on the ground. First coordinate first coordinate frame is attached with the robot body. That is, when you twist your body, the motion will be taking place about what axis? About Z1 axis, okay, with respect to Z0 axis. Z0 is my inertial coordinate frame. You understand, right? So let us put here these two coordinate frame together with another coordinate frame here. This is also attached here, called second coordinate frame, okay. And as you know, the twist or the motion about Z1 axis, vertical motion, so Z1 axis will be my here, okay. So after getting the robot, wherever you find motion, you put your Z axis. That's the rule you have already studied. And then shoulder is moving like this, up, down, right? About what axis? About Z2 axis. So this will be the Z2 axis direction, okay. Just separately we have shown it here. So this is Z2 axis. Z2 axis will describe the shoulder's motion up and down. Now there is, so you need to fix coordinate frame Z. So first all the Z coordinate frames you fix, okay. Z0, Z1, Z2, then Z3. Elbow is moving up and down with respect to this. So you assign a Z axis there and call it Z3, okay. And you see Z4, 5, 6 you assign by seeing this drawing here. So wherever you see the motion, okay, so this is about this axis, there is a motion about, this is, I am calling roll, this is yaw, okay, yaw, okay, and this is again, this is pitch, about this yaw, about this roll. So yaw, pitch, roll, just a name we have given. So this, all the Z axes are now fixed because you could identify the motions and Z axes are fixed. Okay, Z axes are fixed. Now, once the Z axis is fixed, you need to figure out that okay, where is common normal direction? Okay, so here is one Z axis, another, so Z0, Z1. So this is DH table. DH table you need to form, and all the parameters are known in degree, in millimeter, in degree. Okay. So now the drawing is there. You see, this is A2. A2. What is this? This is the distance between Z2 and Z3 axis. Okay. And you see, both A1 and A2, by virtue of fixing coordinate frame, the liberty I had to put initial coordinate from anywhere, I put it here. By virtue of doing that, all this parameter is gone. So this A2 parameter is the distance between two successive Z axis. What is two successive Z axis? Z2 and Z3. So A2 is actually 431.8 millimeter. Okay, so this is the common normal, distance between common normal, characterizing the link length. Now you need to understand, characterizing the link length. So this is the link, its length is actually A2. Now, what is A3? You see, A3 is the, you see, this is A3. So the distance between, you see, Z axis is perpendicular to the plane of this and Z3, and this is Z4. Okay, so they are spatial structure. Z4 is actually so Z1 and Z4. Okay, and that distance between these two z-axis is actually a3. A3. Had it been this, had it been here, then z3, a3 would have been 0. Okay, but a3, that is the um, a3 existence is there because they are offset. Okay, and then since they are offset, d will also come into the picture, you know. So d is the distance between two successive common normal. So one common normal is actually yeah. So this one and this one x1 or x2, x1 and x2 because they are the same. Okay, x2 and x3. The distance between them is d3. So you need to understand. It's very simple, right? So you got a3, you got d3, okay, and then you have the distance between the common normal z3. This is z3 and z3 and you see z4, z3 and z4, z3 and z4. Okay, so this is the d4. Okay, the distance between this is d4, yes, d4, and the d3 is the distance between the common normal. You see the x2 and x3, x2 and x3. Distance between them is d3. Okay, so in this way, the all the dh parameter denoted 13 by parameters are to be determined. Okay, and once you have determined, d4 incidentally is 433.07 millimeter, d3 is 149.09 millimeter, and then you see a2, that is link length, and this is offset, characterizing offset, that is the distance between two common normal. And then you see each and every motion parameter. Motion parameter will be about z. This is a revolute type of robot. They have a range. Okay, and that range will be given by the designer. Means, for example, if you stand on your own feet, you cannot rotate 360 degrees. So every joint, theta 1, theta 2, theta 3, has a range from which is specified here. For example, theta 1 can rotate minus 160 to plus 160 degree. So this is all are in degree. Similarly, all these have a range. So up to this, so far so good, and we'll talk about that once the structure is given, then taking the design data, you are first you attach coordinate frame because you identified the motion. Okay, once you identify the motion correctly, you need to assign coordinate frame, and here you need judiciously to do that. Okay, so that as far as possible, initial parameters should go away, and so that your computation will be simpler. So that's why we did. Okay, 0 and 1 is attached here, 0, 1 and 2 actually attached here. Okay, and so this is the way we have. Once you have coordinate frame, once you have from the designer this data, what is A3, what is D3, what is A4, what is D4, what is A2, what is all kind of DH parameter, and together with the motion parameters range, you put everything in the DH table. Next, what will happen? We will design the model. Okay, we'll figure out the model in the form of matrix, which is very trivial, and I will discuss it in the next lecture. Till then, try to just visualize whenever PUMA robot is given to you, just by making physical motion or seeing the motion, you understand that what is this structure. Once you understand, then you can fix the coordinate frames, okay, following DH principle. That means wherever you see motion, assign Z axis. And then between two Z axis, common normal, you assign X axis. Like that. Between two successive X axis, you assign D. Okay. All kind of thing you know. But specifically to this particular PUMA robot, how generalized DH principle will be implemented, I just told you. And after that, I will develop further model. So this is anatomy because I am dissecting, you see, and this is the PUMA elbow, and it has been drawn here so that beautifully you should know, okay, what is happening here. Okay, so this is great, and in the next class, I'll talk about developing the matrices, which is very trivial. Till then, stay safe. Have a nice day. Bye bye.